Hello everyone, my name is Florian Put. I'm a PhD researcher at Ghent University in Belgium, and this presentation is similar to the presentation that I delivered at the IAFSS conference in La Rochelle in 2026. And it deals with some work we've done on the creation of a probabilistic model for the free thermal strain of concrete, and we did this through Bayesian updating. Now, before going into the details of what we've done specifically, I would like to stress the importance of the free thermal strain in structural fire engineering, because the free thermal strain has the capability of significantly altering the load distribution in a system. And to illustrate this, I would like to do this with just a very simple example. So assume that we have the frame structure as is given on the slide. And we are going to heat up the middle column. The rest of the structure remains cold. Well, what happens is that this middle column wants to expand, but the expansion is restrained by the cold structure. So what happens in the end is that the compressive force in this column is going to increase. And due to this increase in compressive force, it's very likely that we get some plastic deformation. And if we have plastic deformation, it means that the column will get shorter. And if we then cool down again, we could end up in a situation where the column is actually shorter than it initially was. And the column could end up in tension instead of compression. So the free thermal strain is a very important property. So it's very important to also have a good model for calculations. And then secondly, well, because we're dealing with concrete, we know that we can expect quite some variability within the same material. So it's also important that we account for this variability, and this we can do through a probabilistic model. So in this work, we're going to create a probabilistic model for the free thermal strain of concrete. And as a starting point, we've decided to use the state-of-the-art model for the free thermal strain of concrete, and that's the one that's implemented in the finite element software Saphir. Now, in Saphir, the model actually has three submodels. First, we have the heating model, which is basically just the Eurocode model. And secondly, we have the residual model, which is based on some tabulated values, and then they do linear interpolation in between those values. And it has a maximum of 900 degrees, meaning that if you go above, the residual strain actually remains constant. And then in cooling, what they have is they have a second degree polynomial fitted between 2 points, which are the residual point and the point at maximum temperature. Now, for the sake of our work, we have decided to reparameterize this model a bit. So the heating function, instead of writing it as a function of the temperature, we have decided to write it as a function of the temperature increase, delta T. And this gives us three model coefficients, C, D, and E. The values of these coefficients you can obtain by just working out the equation with delta T. And then we also have a fourth parameter, and that's the temperature increase at which the plateau starts. Now, in the real model, they say 700 degrees, but we have taken this as a variable. Then we have the residual model. Now, we decided not to work with the tabulated values, but instead to approximate it with a second degree polynomial. And then we also get two model coefficients, A and B. And we also have a third parameter here, which is the plateau temperature increase in the residual thermal strain model. And then the third one is the cooling model. And in the cooling model, we've introduced the blending parameter R. So if you remember correctly, in the real model, we had 0.6 times TR plus 0.4 times TR squared. And we've replaced this with a blending parameter to give us some more freedom to alter the shape of this curve. Okay, so we have a model, but if we want to update this model, we also need some experimental data. And for this work, we have actually done two experimental campaigns. The first one was done with a radiant panel, our HIFREP radiant panel. And this one focused really on the residual thermal strain. So what we did was we put 4 cubes underneath the radiant panel and heated them up with a constant heat flux for a fixed duration. And we did this for several tests, and every test had a different duration and a different constant heat flux. And then in the end, with a caliper, we actually measured the residual thermal expansion. And you can see the results on the right-hand figure on the slide. So between tests, of course, there's a lot of variability because there are different heat fluxes and different durations. But also within a single test, you can see quite some variability. And that's because it is concrete. We expected such variability, but it is again a testimony to the fact that we really need a probabilistic model instead of just a deterministic model if we want to account for this variability. Then the second experiment is more of a traditional way of measuring the thermal expansion, and it gives us the full thermal strain temperature history and not just the residual one. So what we did was we placed a concrete cylinder in a furnace, and then using 2 quartz glass rods and an LVDT, we were actually monitoring the relative displacement of the top surface as compared to the bottom of the furnace. And we did this at a very slow heating rate of 0.5 degrees Celsius per minute to avoid large temperature gradients inside the specimen. And in the end, what you get is thermal strain time history throughout both heating and cooling, as you can see on the right-hand figure. Now, this figure only visualizes the results of 3 tests. In reality, we did 7 tests. Okay, so we have data, we have a model. Now we also need a framework to actually perform the update, and we have decided to use the Bayesian framework to do this. And the Bayesian framework is based on Bayes' theorem. Now, I think most of you at some point in your life will have seen Bayes' theorem, but just as a quick recap, Bayes' theorem actually tells us that the posterior probability, and this one actually represents the updated belief about the parameter value, can be calculated as a multiplication of the prior probability, which indicates our initial belief about the value of a parameter, and then the likelihood, which answers the question how likely the data is for a specific value of the parameter. And then we have to normalize this by the marginal likelihood, which is the probability of observing the data in general. But this one is usually quite difficult to calculate, so we cannot, for a real application, just use Bayes' theorem. So what we need is an algorithm that avoids the calculation of the marginal likelihood. And this can be done if you use a Markov chain Monte Carlo method algorithm. And in this case, we've used the Metropolis algorithm, which is one of the basic ones. Okay, so one of the prerequisites of the Bayesian framework for updating the model is that you start from a probabilistic model. But until now, our model is still deterministic, so we've decided to assign some probability density functions to the various coefficients and parameters that we have in our model. Now, without going into detail, the mean value is always based on the value of the deterministic model, and the coefficient of variation is actually based on engineering judgment. So we just visualize the result for different combinations of coefficients of variation. And then we decided based on our engineering judgment whether the spread that we got on the results was something that we expected. And based on our judgment, these values are quite good. And well, now that we have the prior probability density functions, we can go to the results. And we will start with the result for the residual model. So for the residual model, we actually have 2 series of test data. We have the data from our radiant panel tests, which is the first data set that we used. And as you can see, if you perform Bayesian updating with this data set, we get useful updates for the parameters A and B. Both of them are shifted to slightly higher values, and they also get a bit more narrow, meaning that we have less uncertainty on these parameters. But for the plateau temperature increase in the residual thermal strain model, the update is less useful. We can see that for the lower temperatures in the plot, there is an update, there is a reduction in the probability of observing these temperatures. But then as soon as we go to really high temperatures above 900 degrees, we see that there's basically no update. It's still constant, and that's because this data was completely absent in, or these temperatures were completely absent in our data set. And then we did a second round of updating where we started from the results of the inference on the read panel test data. So the prior here is actually the posterior from the inference on the HIFREP test, except for the plateau temperature increase, where we just started from a uniform prior again, because the first round of Bayesian updating didn't really give satisfactory results. And what we can see is that the parameters A and B are updated very slightly, much less than in the first round of updating, which means that the values between those tests are quite well aligned. But then if we look at the plateau temperature increase, we can see that we obtained actually a much nicer update than in the first round. But still, it's not completely useful because the very high temperatures are still absent in the data. So it looks like it will be something like a normal distribution, but we cannot be certain yet because, well, we still have these very high temperatures that have not been updated yet. Now, so far, we have only talked, of course, about the marginal posterior distribution. So we have discussed the various parameters separately. But it's also important to consider whether there's some correlation between the parameters. And I can tell you in this specific case, we actually have a correlation between the model coefficients A and B. So if we take a look at the results of the inference on the radiant panel test data, we can see that there is a linear correlation between A and B. And then if we take a look at the results after the inference on both test data, we can see the same linear correlation, but the correlation has become stronger. And this is important because even though the marginal posterior distributions didn't change much by including the furnace tests, we actually have a lot more information because we know the correlation has become much stronger. And this is actually something you can see really well if you plot the results. On the right here, you can see in green the prior or the model based on the prior probability density functions. Then the black lines indicate the intermediate step after inference only on the radiant panel test data. And you can see that then if you go to the real posterior one, which includes both, there's still a lot of reduction in the uncertainty. So the fact that we have a much stronger correlation is also reflected here in the overall performance of the model. Okay, so the second model that we are discussing the results of is the cooling model. And there are two remarks that I need to make first before looking at the real models. First of all, the state-of-the-art model specifies a second-degree polynomial for the cooling model. But if you compare the experimental results with this second-degree polynomial, you can observe that it works well when the plateau temperature is not reached. But as soon as you reach the plateau temperature, the second-degree polynomial doesn't work too well. So we started looking for a solution, and we found a solution by changing the second-degree term to a fourth-degree term. So we just changed the exponent 2 to the exponent 4. And this one actually manages to capture the experimental result, both when the plateau temperature is reached, but also when the plateau temperature is not reached. Then the second thing that's important to mention here is that compared to the previous one, the residual model, in this stage, we don't have single data points, but we actually have a series of data points. And these data points are not independent of each other. They're correlated because they result from a time series. And to overcome this issue, because in Bayesian updating, you need to either account for this correlation, which is quite tricky, or the data points need to be independent. We've decided to first perform a curve fitting to obtain a value of R and then perform the Bayesian updating with the specific value of R. And you can see the results here. So we started from a completely uninformative uniform distribution, and in the end, we end up with a approximately normal distribution that's quite narrow. So this is a lot of reduction in the uncertainty, and this is a very useful result. Now, I will not discuss the heating model in detail because it's very similar to what to the other models, but I will discuss the overall outcome. So we already discussed that the parameters A and B should be considered as a joint posterior distribution to account for all the information. We also saw that for the plateau temperature increase in the residual thermal strain model, there is not really a distribution type that we can fit because part of the update is missing because we don't have very high temperatures in there. And we also saw that for the cooling model, the posterior distribution of R is approximately normal with a mean value of 0.45 and a coefficient of variation of 0.04. Now for the heating model, we get very similar results. So the coefficients C and E appear to be also correlated. So again, here you need to consider them as a joint posterior distribution rather than sampling from their marginal posterior distribution separately. For D, the parameter D, we didn't really obtain a good update. That's because its overall importance is quite limited. And then for the plateau temperature increase, we also got quite a good update. The posterior was also approximately normal with a mean value of around 590 and a coefficient of variation of 0.08. And then what we've all been waiting for in the end is comparing the prior model to the posterior model. So the prior model, for the case where we heat up to 800 degrees Celsius, we've already seen before. But if you compare it to the posterior model, what we can see is that we have a lot of reduction in the uncertainty. Also, the model has shifted a bit from the state-of-the-art model to reflect the behavior of this specific type of concrete. So we have achieved our goal, we have reduced the uncertainty, and we have created a probabilistic model for the free thermal strain of concrete. To conclude, some final notes. So in this work, we've created a probabilistic model for the free thermal strain of concrete, including the cooling stage. This was done for a very normal concrete without any special additives. It's a normal strength concrete C3037. As long as you stay close to this concrete, the results will be similar, but if you deviate very far, then you may need to run some tests and update the model again. We got very good updates for the model coefficients, despite their regression-based nature. And that's very important because they are not real quantities that you can measure. You need to derive them indirectly, but that worked quite well. And then for future work, we should definitely look at furnace test data that goes to really high temperatures, to 900 degrees, 1000 degrees and above, so that we can get a better estimate for the residual strain plateau behavior. And with this, I conclude my presentation. I thank you very much for your attention. And of course, in case you have any questions, you can contact me through the contact details on the slide.